So I will speak about dynamical percolation. And it's linked with sensitivity of percolation, so it will be very dual to each other, and also about harmonic analysis of Boolean function. So this one will be the tool to study the two other processes, and this is a joint work with Gabor Peter, I think, with the pronunciation, and Oded Schramm, both from Microsoft Research. And so there is a paper now in the archive, and it's called the Fourier spectrum of percolation, something like this. So maybe let's first let me introduce the model of dynamical percolation. So it's maybe the most natural dynamic you can do on a percolation configuration. So you start with an initial configuration omega 0. So maybe let me first tell you that the whole talk will be on the percolation on the Z2 lattice at the critical value, PC equals 1/2, and on the triangular lattice on the sides, also at PC equals 1/2. So you've seen these lattices a lot these 2 weeks. Dynamical percolation, you start with some critical configuration, and then you let the configuration evolve with time. And what you do is that for each site, or bond, you update the site or bond according to a Poisson process of rate 1. So Poisson process of rate 1. So the rate doesn't really matter. You could take rate 2, it's the same. So basically what you do is, and you do this independently for every site. So let's say if the configuration at the beginning is something like this, and you start the dynamic, you look at this edge, and maybe after some time it will disappear. Maybe this one will appear, and you will have something moving like this. So if you look at this from far away, and you start with some configuration, so it's a bit hard to draw, but in a radius r, in time t small, let's say, how many edges will have changed? So in a time t, you will not change anything with probability exponential minus t. Right, so things, bonds will be updated with probability 1 minus exponential minus t. which will be roughly t for t small. So in time t, you will have a proportion t of the edges which might change. So in this dynamic, at rate 1, you resampled the sites. You could also just change its value, like if it was open, you put it closed. And it's the same dynamic up to a speed of 2. So it's the same. So I think that's the most natural kind of Markov chains you can build on the percolation configurations. And one of the questions you may ask, so the analogous process that you would have for random walk would be at the limit the Ornstein-Uhlenbeck process. So here it's a kind of Ornstein-Uhlenbeck process on the dynamic, on the percolation, something which keep invariant the critical measure, the measure on the critical configurations with time. And one of the questions is, can you find exceptional times t where there is an infinite cluster so such times they are called exceptional times. Because as you know, the probability of having an infinite cluster at the site 0, say, in D2 or in the triangular lattice, it's something like this, right, with some infinite derivative here, but continuous. And therefore, almost surely there is no infinite cluster, right? So the configuration you start with, you know that there is no infinite cluster with probability 1. But maybe when you look at the dynamic over the time t, maybe it could happen that sometimes the process explodes somehow and you get infinite clusters. So of course the Lebesgue measures of such times has to be 0, but still it may exist. So the usual example they give is look at the uniform measure on the circle and sample a point according to this uniform measure. Maybe it goes here, and ask, do you touch 0 or not? So almost surely you don't, of course. But the natural measures which preserve the uniform measure on the circle could be to start with some uniform point and then to do some Brownian motion on the circle. So it preserves the uniform measure on the circle. And sometimes you'll get exceptional points where you hit 0. And you can even specify what is this set of exceptional times. You can say that this is of dimension of Hausdorff dimension 1/2, and this is the set of 0 values of the Brownian motion, and you can describe this pretty well. And here, well, you look at the property, do you have an infinite cluster? And more precisely, for instance, do you have an infinite cluster at 0? And if you do, then can you describe the set of exceptional times? So if this is the set of exceptional times, the first question is this non-empty? And then try to describe this set. So of course, the bigger the set is, the more sensitive the property is, the less almost sure it is, or things like this. So maybe let me start with an argument with ends which doesn't work, which gives some intuition of what's going on with the dynamical percolation. Start with the initial configuration and look at the function of the time. So take some x in z2, for instance, and look at the function which gives you the diameter of the connected component at the site x at time t, so for omega t. So at time 0, maybe the connected component is like this. So if that's x, d0 of x is this radius. And then let's the dynamic evolve. Maybe after some time, maybe it gets further away. So maybe that would be d t1 of x, because this edge appeared. And maybe after some time, maybe this one could disappear. And therefore, the dt will be smaller. So basically, you could draw the function dt as a process. So dt of x will start at some value until one of the important edges on the boundary or in the middle is resampled, and maybe you change. So here we had some bigger radius at t1, and then we had some smaller radius, and so on. And what you want to know is, if you follow this process, do you have times where there is explosion, where the dt of x goes to infinity? Right, so what's, just to get some intuition, what's going on if dt of x starts being pretty big? So if you start here and you move and you do something and you start being very high at distance r, say. So what does it mean? It means that at this time you have some big cluster attached to the vertex x, or the edge is x, it's the same. So it means that at time t you have a so if I write it schematically, this will be some big cluster like this. And if you follow the Pierre's course, or I don't know, Wendelin's course, you know that from very far away at criticality, this looks like a fractal set. And you will find many points here which, if you touch one of them, you disconnect the site x from distance r. So if in the dynamic you touch one of these, the distance will decrease, will do a big jump. But on the other hand, you also have a big cluster, microscopic cluster touching these, right? And these big clusters, they touch this one with many points like this. So basically, there is a competition between touching these ones and going further away, or touching this one and decreasing. And how many such points do you have? If you are at distance r, these are pretty much clusters of distance roughly r. So these points are called the pivotal points. So these points, locally, you have some open paths like this, and some dual paths like this. So what you have is a point here, something like this, and something like this. And we know, at least in the triangular lattice, that the probability of such an event to distance r is about r to the minus 5/4. And something which is sometimes annoying, there are some logarithmic corrections. Well, we don't know if there are, but there could be some logarithmic corrections. But the exponent is 5/4. So these points, they have probability r to the minus 5/4. These ones are the same. So basically, the number of these points is that's a pivotal point, this. The number of pivotal points at these scales of r, you have r squared points. Each of them have this probability. So at least in expectation, the expectation of this is in so it's about r to the 3/4. Right, so it means you have many, many important points which might make a big jump here, or a big jump like that. But the point I want to make is that it's very fast. Why? Because you have many points, so until what amount of time do you have to wait before you touch one of these? So this is all of this is very sketchy because, of course, everything is sort of moving, so it's only with hands, but you will have to wait. So in time t very small, things change with probability t. That's what I said before. So if you have this, it means you have good probability to not touch any of these, and basically the picture will stay. You won't have a big jump like this, but as far as you have this, you start touching pivotals and you may get a big jump. So basically here, the amount of time that you will wait, the delta t here, will be of order r to the minus 3/4, and you'll do a big jump. So of course it's only approximative because the boundary of the cluster here has much more points than r to the 3/4. So there are some small fluctuations here, but you almost don't see them. And then you do a big jump. And basically, so these are macroscopic things. So if you would like to follow the process, you would look at a logarithmic scale. So you would look at some process dt of log of dt of x. And you would ask, does this walk, which is unfortunately not at all Markovian, does this walk goes to infinity sometimes or not? So if you can understand what's going on here by seeing that there is some drift to infinity somehow, that you have more chance to touch these things rather than coming back close to 0, and that there is some drift in this non-Markovian process, then maybe you can prove that there are exceptional times. But this turns out to be hard because this is not Markovian at all. You need to remember what was exactly the picture. And it's not easy to compute the drift or things like this. So actually, that's not at all the way we will look at the problem, but at least it gives some first intuition, which says that once the cluster starts to be big, things start to move pretty fast. And maybe you have a chance to have explosion. So what is the way to prove that such exceptional times exist. That's a second moment argument. So how does it work? So that's something very classical in probability. Let's look at this thing, the amount of time that you spend at distance r. So you start with some initial configuration, and you look at the dynamical percolation for time 1, and you look at how long did you have a link between 0 and r. And so the first thing that we can say on this is that the expected time where you stay at this distance is easy to compute, because that's the integral from 0 to 1 of the probability that 0 is connected to distance r at time t. Right? But the dynamic, the critical measure is invariant with the time, so this is just integral from 0 to 1 of this probability at time 0. So this is just the probability. Right? And what is this probability? This is one of these critical exponents. So I stated one before, which is this one. And we'll need another one, which is the probability that you go to distance r. And that probability is r to the minus 5 over 48 plus a little o of 1. So, and maybe we'll write it first exponent like this, and this one we'll write it the fourth exponent. Oh, good point, yes. So these values here, indeed, we know them only for triangular lattice. And for Z2, we don't know these values, and even we don't know that there is an exponent. So you might think that we don't know much, but still we'll be able to prove the existence of exceptional times for Z2. But for Z2, we have to stick to these notations, because we cannot say much more. Okay, so the first moment of the amount of time that you spend is the first critical value, right? And now there is a general principle which says that if you manage to control the second moment with the squared of the first one, then you're in good shape. You can prove that this random variable is not degenerate or something like this. So why that? It's easy to see, so it's just Cauchy-Schwarz. You look at this, and you apply Cauchy-Schwarz like that. So, of course, this random variable is positive, and therefore it's less than this. So what the second moment tells you is that the probability that your random variable is positive is more than this divided by this. And if you've never seen it, then maybe you should keep this in mind because it's useful. So if we manage to prove this, that the second moment is bounded by a constant times the square of the first one, then we'll prove that this probability is bounded below, independently of R. So you can let R go to infinity, and it will mean that if you take something really big, you will spend some time, maybe very small, but where the zero will be connected very far away. And letting R go to infinity, you can prove with some capacity argument, or at least you can be convinced that there are exceptional times. So the main goal, at least for the existence, is just to prove this. So, well, let's write what is the second moment. So m of r was this integral here. So m of r squared is just this double integral. And you want to be connected to r at time t, time s, and at time t. So ds dt. So you can write it, can put the expectation inside, and that's the probability to be connected to r at distance at time s and being connected to r at time t. But since the measure is invariant, it's the same as looking at this. So basically, you can rewrite this as less than that. So the second moment, it's an integral of these correlations probability. So if you have a good control on these correlations, maybe we'll be able to prove what we want. Well, maybe I should write it with the probabilities. So what we want is that the integral of this correlation is less than the probability squared. And if we manage to do this, then that's over. So the whole game is to understand the correlations of these percolation events. So before starting all the machinery which will go through these harmonic analyses and things like this, I'll give you a heuristic which explains how to compute this correlation. So how to compute that? So let's assume, it's not necessary, but let's assume that we have this and some time very small. So if you want to have both a cluster of size at least r at time 0 and at time t, then you need to get it at least at time 0. So we have well, I should do it big. the omega 0 configuration and the omega t configuration. And we go to distance r. So let's assume that we have a path here from 0 to distance r. And now let's move the dynamic a little bit with this time t very small, and let's ask, do you still have some path going from 0 to r? So you might have destroyed it somewhere because the percolation moved. But using the argument I said before, until some distance x, the number of pivotals, important points that you would need to touch to destroy the link is too small for the time t. So there is some distance here which depends on the time t, where the picture is kind of frozen. So here, so we'll compute this distance x in a second. But what I'm saying is that here we will still have this thing. And now, after this threshold radius, somehow, where things are frozen inside, outside we start touching important points, which we start destroying or helping the percolation to cross between these between radius x and radius r. And what we will see is that it starts touching pivotal, and actually it will be completely independent. So basically, omega t is a noised version of omega 0, where each edge is resampled with a probability roughly t. This is this 1 minus exponential to the minus t, coming from the Poisson process. And so this is a noised version, and here you start touching pivotal, and long connection properties start being completely independent. So somehow, until this threshold distance, you keep all the information, and what we would like to prove is that after that, you lose all the information and things start being independent. So of course, nothing is justified here. So what could be this threshold x? So let's say between x and x over 2, you have about x squared sides. And as I drew before, the number of pivotal points is of expectation. Pivotals is of expectation x squared times this 4 arms exponent that we had before. So this is up to little o of 1, but let's not be too precise here. So it is in x to the 3/4. And we want that until radius x, things are pretty frozen, so we don't want to touch pivotals. So it's enough that t x to the 3/4 is less than 1. If you have that, then you don't touch important points until distance x. So if you compute this, the threshold distance is 1 over t to the 4/3. So at least until that distance, if you already had an arm from 0 to r, you will still have an arm from 0 to this distance. And actually, this argument is it doesn't look like this here, but it's actually rigorous. It's easy to make sense of it. what is much harder is to say that after that distance, then things start being sensitive. So to resume, what this heuristic says is that the probability to be connected at time 0 and at time r, well, first, you want to be connected at time 0. So there is a probability at time 0. And what remains to be paid somehow for still having a crossing here? Well, you know that you should still have, you should still be in good shape until that distance. And then what will be hard to prove is that here you are completely independent. So what remains to be paid somehow is the probability to go from radius 1 over t to the 4 thirds to distance r. So the heuristics gives a formula for the correlation probability. And as Pierre explained, I think, did you explain quasi-multiplicativity? Quasi-multiplicativity? Okay, good. Yes, so I will remind, actually, the statement here is simpler than for the forearm, but basically quasi-multiplicativity it tells you that the probability to have 4 arms between distance 1 and r, this is up to constant, the probability to go from 1 to some intermediate radius, and you can choose whatever radius, and then to go from little r to big R. So, and this you prove it saying that typically arms are well separated, so you can glue things together, you can glue scales together. And here what we use is this one. So this is true for any number of arms, but this one is much easier to prove. You don't need the separation of arms. It's basically this observable is an increasing event. It's only having an open arm between 0 and distance r, so you can use Russo-Seymour-Welsh. But basically, you can cut scales like this. So if you apply quasi-multiplicativity here, what you get is that the correlation, so I won't write it again, is alpha 1r squared divided by this one. And now you can use the fact that that I stated before, that the first arm exponent is 5 over 8. So if you plug in here, what you get is that this gives you 4 thirds times 5, 8. So this gives t to the minus, so 4 thirds times 5, 48 is 5 over 36. And this gives you t to the minus 5 over 36 times this. So, and this we are happy to have it because this is exactly this probability squared. And now what you see is that t to the minus 5 over 36, this is integrable. So if the heuristic was true, if this is indeed has this behavior, then and you integrate, you get a finite value times the first moment squared, and therefore you prove existence of exceptional times. So maybe I'll do one or two remarks here. Well, maybe I should have kept this. Notice that there is this 5/36 that comes in. And maybe, Pierre, you already explained this, but the theta function behaves like that near PC. So I don't know if I stated it before, but you know that at least for the triangular lattice, the density of the infinite clusters behave like this. Theta of P is P minus 1/2. That's this exponent which makes the derivative infinite at the critical value. And actually, this 5/36, it comes from the same kind of argument, where you start with a critical configuration, and you want to know what is the probability that 0 is connected to infinity at the probability P. And what you do is, instead of doing dynamical percolation, which preserves the critical measure, each edge, now it evolves with a Poisson clock or something like this, and each time the clock rings, instead of resampling the edge, you put it open. And doing so, the dynamic leaves the critical case and enters the supercritical percolation. And if you do this dynamic and you go from there to there with a small t, the same argument will tell you that things don't change so much until this reduces x. So if you want 0 to be connected to infinity at some small value p, I mean p just a bit more than 1/2, then you need to get this already at criticality, and this gives you this probability of, probability of connecting 0 to 1/t to the 5/48, to the 4/3. And here t would be the p minus 1/2. And this gives exactly t to the 5/48, to the 5/36. And then the argument will say that after that distance, you start touching many pivotals, but in the open way. So you start having more and more open sites. And actually here, from here, you start having an infinite component. You start being really in the supercritical case. And here you have things, starting here, you have things going to infinity. So the same argument gives you the behavior near 1/2. But the way to justify that it works is different. Here you need to say that after this threshold radius, you go to infinity, and before we need to say that after the threshold radius, things are independent. And that part is more classical in the sense I don't think it needs any harmonic analysis. And the independent statement is somehow harder to achieve. So that's the first remark about the heuristic. And the second remark is that we managed to get heuristically a correlation like this. And the only thing we use to say that we indeed have exceptional times is that this is integrable. But maybe this is a very precise behavior. We can say more. We can say more than just we have exceptional times. And this 5/36 actually tells us that the dimension, the Hausdorff dimension of the set of exceptional times is 31/36. And that's not, well, knowing that we can prove such a precise decorrelation in time and space, that's not hard to achieve. It's just through the Frossman technology. So basically, you need to put a measure with good energy on the set of exceptional times. And what you look at instead is the integral from 0 to 1 of the indicator to be at time s and at time t, but divided by t minus s to some exponent, ds dt. And if you show that this energy is finite asymptotically, then it proves that, so if and to get a probability measure, you need to divide by this thing. And if you can show that well, something like this is bounded, the energy is bounded, then Frossman tells you that the dimension, the Hausdorff dimension, is at least more than 1 minus this. No, is more than gamma. So the Frossman lemma or technology, I don't know, is a very useful way to get a lower bound of the dimension. Because in all of these things, it's usually much easier to get an upper bound. And what this precise decorrelation tells you is that if you plug in this Frossman energy or whatever, then for gamma less than 31/36, you get a finite quantity, and therefore you have at least dimension gamma, and gamma going to 31/36, you get a precise result on the dimension of exceptional times. So maybe it's a good place to state what are the results, at least for dynamical percolation. So the existence of exceptional times on the triangular lattice, it was already proved by Schramm and Steiff a few years ago. So Schramm and Steiff, they proved that on the triangular lattice, exceptional times are non-empty. And actually the way that, so usually the way to prove these things is actually to prove that the dimension is positive. And they prove that the dimension, the Hausdorff dimension is in this interval. And they proved some other things about upper bounds on other exceptional events. And for Z2, the equation remained open. And what we could do with this spectrum of percolation, we could prove that the upper bound that they conjectured to be the good one indeed is the good dimension. So with Pitt and Schramm, on the triangular lattice, the dimension of exceptional times is 31 over 36. And we could prove some other exceptional events, like we could prove that well, let's note it like this, that you have times where you have both an infinite cluster coming to 0 and an infinite cluster in the dual lattice. So remember that with percolation, we often say that PC equals 1 over 2 is the critical value, because it's hard to conceive that you would have both an infinite cluster at PC and one in the dual lattice. But still, it happens that you do have exceptional times where both infinite clusters live together. And the dimension of these, we believe it's 2/3, but we can only prove it's more than 1 over 9 for a reason I will explain later. And so this upper bound was achieved by Schramm and Steiff, but the lower bound no, and therefore they couldn't prove the existence of such times. And well, there are various of exceptional events that you can find. For instance, having an infinite cluster in the upper half plane or things like this that you can compute. And the other result was that on Z2 there are some exceptional times, and the dimension is strictly positive. So that's not at all surprising, of course, because everyone believes that Z2 and triangular lattice should be the same. But since we don't have exponents, the techniques happens to give it anyway. So now the main purpose is to try to explain that above this threshold radius of 1 over t to the 4/3, things starts to be independent. So what we had here is we had this radius and an omega 0 configuration. And I mentioned at some point that we can look at the omega t configuration as a noised version of this one, because here each edge evolved with this Poisson process, but the time t is very small, so the probability that this one was resampled between time 0 and t is probability to be resampled at least once. It's 1 minus exponential minus t of t. So there is nothing deep here. It's just by construction of the dynamical percolation. So we want to say that if we have a path here, and so knowing that we have something connected 1 over t to the 4/3 to distance r, can you predict that you still have such a crossing at time t? And we want to say that no, we can't predict it. It starts being completely independent. So this, to study such things, we will speak of sensitivity of percolation, meaning that how percolation is sensitive to such type of noise. And maybe this radial setting is hard to get at the beginning. It has less symmetry, so we look at a simpler setup at the beginning, which is the usual left-right crossing of a rectangle. So let's say we are on Z2 and take a box R by R to keep the same scales as we had before, and sample the percolation and ask, do you have a crossing or not? So maybe you have some crossing. And that's the omega R configuration. And now apply some noise to the configuration, where for each edge you resample it with probability epsilon, or if you prefer, you inverse it with probability epsilon. So each edge independently, you change it with probability epsilon, and you get this, where each edge is resampled with probability epsilon, and you want to see how this observable is sensitive to noise. So if this denotes 1 if there is a left-right crossing, and -1 if you don't, then you want to know what is the expected value of this, knowing this. So it turns out that if epsilon is fixed and R is really big, then you lose all the information. So it means that you just keep this, or you keep this if you have a square, because the expected value is 0. So it means that when you take a macroscopic box and you do some noise, which doesn't depend yet on the size of the box, then you lose all the information. Another way to write it, which we will use, is that the expected value, just write it as a correlation. Minus this. This converges to 0 when R goes to infinity. And if so, in our radial setting, what's happening here is that the noise here kind of depends on the scale, so it's not a fixed noise epsilon. The T depends on how far you are and things like this. So it's important to wonder about how sensitive it is. So what happens if epsilon depends on if the noise depends on the size of the box? So you may ask for which epsilon R going to 0. We still have what's called noise sensitivity. So in the first step, I'll try to make rigorous what I said before, which is until that reduced, things are frozen somehow. So we'll prove that if epsilon r is much less than, remember this thing, this was with this, then things are stable. And that will be easy to see, so that's why I said that the frozen part is easy to control. What will be harder is to say that if the noise is much bigger than this threshold value, then things will be completely sensitive. So how to see this? Start with the R by R. In the setup I had here, it wasn't necessarily a square, but doesn't really matter. So start with this, with some configuration. And let's imagine that you have a crossing. There is probability 1 over 2, 1 over 2. To be precise, it would be like this. So let's say you have a crossing. And now you want to produce the noise configuration. So you want to produce this one. Noise configuration. So how many edges will change here? So each edge changes or is resampled with a probability epsilon of r, and you have r squared edges. So the number of edges which change is of order r squared times epsilon of r, right? So of course, if the epsilon of r is much less than 1 over r squared, you don't even change anything. So then it's easy to see that this is stable. That's the number of edges that you change. And the way to go from this configuration, from omega r to the noise configuration, is to choose the edges one by one. So let's choose the first edges that we will change. So for this argument, it's maybe easier to do the dynamic where you, each time the clock rings, then you just change the value. So let's change the first edge, E1, and let's look at the event A1 that E1 destroyed the crossing. Okay, so, well, destroy is maybe a big word, but the crossing. What is the probability of this event? So you take one edge uniformly in the square and you change it. What's the probability that you don't have a crossing anymore? So the probability is that you get 4 arms if that's the edge, like this. So the probability is that the edge is pivotal. So of course you may have boundary effects, which is here the probability to be pivotal is not exactly, but it turns out it doesn't really matter, because pivotal points prefer to be in the middle somehow. So the probability that the first edge changes thing is of order that. And now you change the second edge. So maybe the picture changed, but it doesn't matter. What you still have is an ID percolation probability 1 over 2, 1 over 2. So the probability that the second edges changes something. So I should say, rather than this, I should say the probability that the east edge changes something. This probability is still of order that. So the probability, once you change all these r squared times epsilon r edges, that you change something meanwhile, so that you don't have this anymore. It's less, well, it's less than the probability of the union of this thing. So you can just bound this trivially by the sum, so that's less than this. Therefore, if epsilon r is much smaller than that, you cannot change macroscopic things in the noise version, and this is stable. So now what we will prove is that if the noise is much bigger than that, then this is noise sensitive. So there is a threshold at this here. And notice that all these things are true if you are on D2, right? I didn't use exponents. But if we were on the triangular lattice, we can write it as that. So this problem of noise sensitivity of the left-right crossing was started with maybe I will give the history of this noise sensitivity after. And I will introduce what we use to prove such sensitivity results. So this left-right crossing, or the radial case before, all of these are Boolean functions, functions which depend on bits. So we can look at functions f. Well, maybe before I should give a simple example of a Boolean function which is very stable. So a stable Boolean function. So just take the example of a random walk and ask if the random walk at time r is positive or not. So this depends on r bits. And take the Boolean function on r bits, which tells you is it positive or not. Right? Now, if you noise a little bit your random walk, so let's say you do an epsilon noise, basically you will be here at distance square root of r. And if you do, so if you change a fraction epsilon of your choices, you, well, seen from very far away, basically what it is, it's a Boolean motion. And you do the Holstein-Lundbeck process of time epsilon. And at the end, you move over square root of epsilon, so you don't move much. And basically, everything with white noise kind of observables, they are stable when you noise them. So if you know that you are positive and you noise the r bits, then with big probability, you will still be positive. And the percolation is very different. If you know that you have a crossing and you do some noise, then you lose everything. So what is a good setup to to study these equations. It's to look at it more generally and to look at the space of function f from R bits into R, to look at it as the L2 space, and to do a Fourier analysis on these things. So when you want to do Fourier analysis, the first step that you need to do is to find the natural basis for this space. So there are several ways to find the same natural basis. You could look at the group, this abelian group, and to look at the characters of this group, so the morphism from this into the complex numbers. You could also do the its equation on the hypercube. And I guess many other natural things would give you the same orthonormal basis. And the basis that I will use is indexed by the subsets of this. So for each subset of this, look at this function. So you have 2 to the n, so this gives 2 to the n functions. And they are orthogonal, so maybe I should say what is the scalar product I put of this. Well, I'll use the natural one for the probability, so just the expectation. So it's easy to see that these 2 to the n functions are orthonormal, and they are of norm 1. So by cardinality, this gives you a basis. So this is a basis. So now that you have this basis, you can decompose any Boolean functions from n bits into R on this basis. And therefore, you have Fourier coefficients. So these things are called Fourier-Walsh coefficients. So thanks to this, you can write f in this. You can write it as a sum over the functions. Of this. Okay, so what is the expression of the Fourier coefficient? It's just the scalar product of f with this guy. So here it's really like if you had periodic functions on the circle and you take the basis of sine and cosine, and you decompose on this basis, it's the same. And why is it natural to do such a thing? It turns out that the spectrum, these Fourier coefficients exactly give what we want in terms of noise sensitivity. So if you look at the Boolean function on n bits and the Boolean function on these n bits with some noise epsilon. So if you look at this and you want to compute this correlation, so we'll compute this correlation later for the indicator function of the left-right crossing or radial indicator function. So let's write it down. So this is the expectation Now we decompose f on this basis here. So this is a sum of a subset of the subsets of the n bits of this, that times this. But here we have the noised configurations. So now the good thing is that chi-s and chi-s prime, they are orthogonal. So when you expand this, you find that this is just the expectation of this. And now, the only thing we need to compute is the correlation for these simple functions. So, so that's sum over S of the Fourier coefficient squared So let's take S to be some singleton. So just to see what's going on. So if S is just some point somewhere, what is chi-s of omega n? This is just plus or minus 1. It depends on this bit. So the correlation, this is just and this one you resample it with so maybe I should write it. You resample it with probability epsilon. So with probability 1 minus epsilon, you don't resample anything. If xi was minus 1, this one is still minus 1, so this gives 1. And if it was 1, it gives 1. So if you don't resample, you get 1. And if you resample, then if this one is minus 1, the other one is either 1 or minus 1, since you resample, so it gives 0. So that's 1 minus epsilon. That's the correlation you get for sets of the size 1. And now if you have n independent, k independent bits, what you get is the same correlation, but to the k. So all of this to say that this gives you sum over S 1 minus epsilon to the size of S. So you can write it differently. You can write it as the sum k equals 0 to well, n of 1 minus epsilon to the k and, well, maybe we don't need to write it like this now. So what this formula says is that the correlation function between n bits and the noised version of the n bits, it's the sum of the Fourier coefficient squared times this. So now to give to have some more intuition, let's assume that f has L to norm 1. So for instance, if f was the left-right crossing, and we assumed it was in a plus or minus 1, and that's why it's convenient here, then by definition, the L2 norm is 1. And what's nice about this is that Parseval tells you that the L2 norm squared so Parseval tells you that the L2 norm squared is sum over S of this squared. And if we have such an indicator function here, that's just 1. So in that case, we can introduce, or we can see this Fourier decomposition as a probability measure on the subsets of the n bits. So we can define, allows us to define a spectral, probability measure that's not canonical. So this is on the subsets of the bits, and this gives mass. So the probability that, so in the remaining of the talk, the law of the spectrum under this probability will be, I will write it like this, and this probability will be the squared of the Fourier coefficient. So now I can rewrite the correlation function omega n epsilon as sum over S of these, or also as the sum over k of 1 minus epsilon to the k probability that the spectrum is of size k. Okay? So maybe I can just exclude one of these terms, which is, there is a spatial function, which is the spatial coefficient, which is this one, which corresponds to the projection and the constant function. So this is just the expectation. So basically, the probability to get the empty set, this is the expectation squared. And if you plug in this formula, this just tells you that the correlation, as we like to write it usually, minus this, this is the sum of the non-empty spectrums of this. So now when we want to understand the correlation of a Boolean function under noise, if the spectral measure happens to be supported on very big sets, and only on very big sets, then the correlation will decrease very quickly to 0. So if the spectral measure is complicated in the sense that it is on big sets, then it's very sensitive. And on the other hand, if it's supported on small values of k, on small of sets of small cardinality, finite cardinality, then when epsilon will go to 0, the observable will be completely stable. So this dichotomy between stability and sensitivity, this has to do with where is the spectrum supported. So let me give you a few examples. So maybe if you just think of the usual harmonic analysis on the circle, you know that if you have a smooth function, then the Fourier coefficients, they decrease very fast. And when you have a smooth function on the circle, you would guess that if you take some point randomly on the circle and you move it a little bit, then things will be pretty stable. But now imagine you take a function on the circle, which would be sum for n bigger than 10,000 of a, well, I don't know, I didn't try it, but of a sine of nt. So something which would have a spectrum far away. Then it would be something very rough, close to almost the white noise somehow. And if you go somewhere and you change the value a little bit, it will be completely sensitive. And here that's the same idea. If you have a big spectrum, then you lose the information. So let's take a few examples of Boolean functions to get some intuition of what's going on. So if you take n bits and you do this, just the random walk, so I use this so that the norm of f is 1. Therefore, it indeed gives the probability measures on the spectrums. And by definition, you can see that this is already an expansion. This is already an expansion on the basis we had before. And f of the ith bit, it is just 1 over square root of n. Okay, so the probability for this Boolean function to get a singleton, this is just the uniform probability and the singleton. And this Boolean function, it was basically at the limit, it's the place where you are for the Boolean motion at time 1. And I said that when you do the Orstein-Lundberg, when you noise this a little bit, basically this is stable. It doesn't move much. Okay, so this has to do with the fact that the spectrum of this thing is concentrated on very small sets, and even on sets of size 1. So we could do we could build an example of something sensitive by looking at x1, x n plus k. And one way to have it a little bit more sensitive is if it depends on more bits. And now we already have an expansion, but this time it is supported on sets of size k. So typically the spectrum, if you sample it, and you have from 1 to n plus k, the spectrum, it will be something of length k. Okay? So for instance, if you take k going to infinity, but small enough so that you still get Brownian motion at the limit, you get a Brownian motion which would be sensitive to noise somehow. Except that the sensitivity is localized because the spectrums collide 2 points. But it's an easy way to produce a sensitive function. Now you can take, well, actually the worst function you can imagine is this one. just you take the product of everyone. So somehow this is a parity function, right? If you have an even number of -1, it gives you -1, and the parity function is very sensitive because here, well, it's obvious it's very sensitive. If you had to do a voting scheme, and instead of looking at majority, you would look at, do you have an even number of people or odd number of people? It would not be a great way to select people. So that's the most sensitive you can find, because the spectrum is just the whole thing. And now we would like to look at two Boolean functions. The one, so it will depend on the m value, m being roughly r squared, and it will be this plus or -1 depending on if you have a crossing from left to right. And the other one will be the one depending on all the sides in this. And here we'll take 0, but we'll take 1 if we have a path from 0 to distance r, and 0 if we don't. So we could have chosen to have 1 and -1 as before, but this breaks the symmetry. And it gives crazy formula. And here the only disadvantage is that it doesn't give a probability measure. But if you want to have one, you can always, what's the name? Renormalize to get a probability measure. So what we'll try to do now is to look at the spectrum of these Boolean functions, and more precisely how big it is. So starting now, we could only look at the law of the size of the spectrum of these things, but it will turn out that this will be useful, if not necessary, to think of them geometrically, as you would think of the set of pivotal points or things like this. So we will be only interested in the size, but we will look at them as subsets of the square. And maybe now I should give do we need to stop at some point for the? Oh, I thought it was not even 4 now. So. Okay. Great. So maybe well, it's up to you. So how much time do I have? Yeah, if I can talk more, if you want, then we can stop. Because 20 minutes, I won't say much. It's up to you. Yeah.